So make sure you are preparing for next week's quiz and that you are doing those Canvas assignments. All right, we are going to jump into some thermochemistry. Actually, before we do, let me just do a quick kind of review question from our real gas laws. These lines represent the distribution of molecules that are going a given speed. And I have gas A and gas B. And one of those gases is, let's say, methane. And one of those gases is neon. Which one is which? So neon is Ne. What's the formula for methane? CH4. Okay, so to answer this question, what do we have to know about those two gases? Their molar weight. Okay, so what's the molar weight of neon? That's the easy one. Just look on the periodic table. Okay, so right about 20. And rounded to a whole number, what's the molar weight of methane? 16. Okay, so now we know their masses. Methane's a little bit lighter. So which one is methane, A or B? How many people say B? How many people say A? And the rest of you are too chicken to answer. It is B. Yes. Okay, so remember that the lighter weight something is, the further it is to the right here, because that's the faster speed. So we don't really care how tall the hill is. We just care how far over to the right it is. Now let's get into some thermochemistry. New chapter. I'm going to get a new piece of chalk. Thermochemistry is about changes in energy during mostly chemical, but we do look at a few physical processes. So we used to do 2 labs that covered this, and the easier lab covers the more physical processes, so it has less to do with chemistry. But the one that has to do more with chemistry is a little bit more challenging. So I can't remember which one we decided to take out. But one of those 2 labs you're going to be doing next week. Okay, so first thing we need to know about thermochemistry is the first law of thermodynamics. So physicists will call it thermodynamics instead of thermochemistry because then it doesn't have the word chemistry in it. But basically, dynamic means change, so that's where the change comes from. Okay, so the first law of thermodynamics is very similar to conservation of mass. It is just abbreviated as conservation of energy. And anytime we say we are conserving something, we're saying that before and after we do something, usually a chemical reaction, that thing that we're conserving is the same. So we have conservation of mass before and after a chemical reaction, the masses are the same. The mass of the reactants is equal to the mass of the products. So with the law of conservation of energy, it's the same thing, only it doesn't just apply to chemistry, it applies to all processes. So the conservation of energy applies to everything, all processes. But instead of measuring just what's going on with our reaction, we are looking at the entire universe. So in all processes, the total energy of the universe is unchanged. But we can have changes of what kind of energy we have and what has the energy. So energy can be transferred, so from one thing to another, or transform. So sometimes you will hear this process or this law stated as you can't win, because pretty much everything that we do relies on us having some kind of energy. We have whole economies based upon how we get energy, whether it's fuel for our cars or electricity for our houses or whatever. So we want to get energy to be able to use it. But that always comes at using up energy elsewhere. So we can't make more energy than there currently exists in the universe. So we say you can't win. You can't get more energy than you put in. So sometimes people will talk about things like, say, a hydrogen-powered car. Okay, so if you have hydrogen as your fuel, you get a lot of energy out of that. So that's really great. It only produces water as a byproduct, so we're not getting more, particles and more carbon dioxide in the atmosphere. But the problem is it takes a lot of energy to make hydrogen in the first place. So we have to find a way to get the energy that we put into our cars and so forth. So there's really no way that we can do it that we come out ahead. Now, there are some ways that are more efficient than others, and that's what is the goal, is to get the more efficient ways, but we're never going to make more energy than we started with. Okay, so kinds of energy. If we are transforming energy, we're going between different kinds. So usually people will break energy down into two categories. Either we're using it or we're saving it for later. Motion, kinetic energy is being used. Potential, we're storing it for later. Light is also a form of energy, and it's really kind of hard to put it into one of these categories. It's kind of being used, but it doesn't follow that same rule about 1/2 mv squared because there's no mass to light. So I'm just going to kind of put this over here and say, yeah, light's a form of energy too. So we can have lots of things moving. We can have objects. That's what we would study in physics class. We have something that's falling from a 3-story building and how much speed does it gather and that kind of thing. But we can also have molecules. So if molecules are moving, you might have sound. So if you've heard of a sonic boom occurs when an object, usually a plane, is going faster than the speed of sound. So the motion of that plane, the plane arrives to you before the sound that the plane was making and the air that it was moving when it was further away. And so you end up with this boom, and it actually has some physical energy associated with it. But all sound has some energy. It's moving your eardrums and that kind of thing. And then we also have heat. So heat energy is just molecules moving. So those are the big ones. Let's see, do I have any others in here? Oh, yeah. One kind of energy that is talked about in physics a lot is work. So again, this is objects moving, but we talk about the work that is being done. For chemistry, that's usually gases. So gases can expand or they can contract. And so in your car, they might move the pistons in the engine, and that does work that helps propel the car forward. And then electricity is just moving electrons. Those are all forms of kinetic energy. So we can move around between these different kinds of kinetic energy, or we can move back and forth with light or potential energy. So our stored energy has fewer forms that are more broad. So we might have gravitational, which you talk about in physics. And this is the potential energy that you get from an object just being up high. If you let go of it, it's going to start moving. So it has the potential to turn into kinetic energy. If something is lying on the ground, it has very little potential energy. It can't really go any lower. So that is one kind of potential energy. Another is elastic. So you can think of like a spring or a rubber band or bond vibrations. Okay, so we think of the vibrations of bonds as being like springs. So there's some potential energy in that. And then we have electrostatic. And this just means that if I have two charged particles that are near each other, either they're opposite and they're going to come closer together, or they're like and they're going to repel. So two charged particles will cause each other to move. And then we will broadly talk about chemical potential energy. But that chemical potential energy kind of encompasses some of both the elastic and the electrostatic potential energy. So there's some overlap there. Okay, so those are different kinds of energy. The first law of thermodynamics says that if I have light in this room, it didn't just magically appear creating more energy in the universe. It had to come from somewhere. That probably came from the electricity. That electricity probably came from a power plant where maybe they were burning. So there's heat, some chemical like coal, and that coal was formed from dead animals that maybe had plants that had light from the sun. And ultimately, most of the energy that is in play in the universe right now goes back to the sun. Somehow the sun shined light on the earth, plants grew, and things happened, and now we have whatever energy we have. So that's our various kinds of energy. Energy is basically the ability to either move something or warm something. So all of these forms of energy can ultimately be applied to our kinetic, our motion, the potential mostly have the ability to create some motion, or they have the ability to warm something up, like light can warm you and heat, of course, can warm you. So that's what our energy is. Let's see. Your book makes a note of this, so I'm just gonna, this is kind of a side thing, but I'm gonna put it in here because your book talks about it. So during chemical reactions, we know mass is conserved. During nuclear reactions, so this is stuff that's going on either building up a nucleus or breaking down a nucleus. During those nuclear reactions, small changes in mass create energy. So you probably have seen or heard of Einstein's equation equals mc squared. So it's really delta E, the change in energy, the amount of energy that comes from this is coming from a small change in mass in the nucleus times the speed of light squared. Now the speed of light is 3 times 10 to the 8 meters per second. So if we square that, now we have 9 times 10 to the 16th. So that's a huge number, right? So we're talking quintillions, I think, at that point. So even if I have a very, very small change in mass, I can still get some energy out of that. And that's why nuclear power plants and nuclear bombs and whatnot create so much energy. So where does this come from? If we look at the mass of a proton, so basically the mass of a hydrogen without its electron, and we add all of those up, we add up all of those masses, and then we add up all of the masses of the neutrons in any given atom, the mass of the atom itself will be a little bit less than the mass of all of those things. It's going to be less than the sum of its parts. And that difference in mass is called the binding energy. And so that's what the delta E is. So for our purposes, we assume that mass and energy are separate. But when we talk about the law of thermodynamics, and we say, well, the energy of the universe is constant, we include mass as kind of a form of energy because this is essentially creating energy here. So that change in mass, creating energy, we're including mass as part of that energy. That's not really going to affect anything we do in this class. But, you know, your book talks about it. So we're going to mention it. Okay, so let's talk about temperature because thermo means heat. So temperature from our last chapter we know is proportional to kinetic energy. And the kinetic energy of any given thing we know is equal to 1/2 mv squared or u squared if we don't want to confuse it with the volume. So v is velocity or speed. So we know the faster things move or the higher the temperature. So this is mostly going to be in the form of vibrations. The solid particles aren't traveling from place to place. That's not the speed we're measuring. It's them wiggling in place. And that wiggling in place is we're measuring how much wiggle they have per second is where that comes from. So most solids and liquids have the tendency to get larger as they get warmer, and we call this thermal expansion. So in lab, we usually use digital thermometers, and in a more complicated way that connects back to this. But if you've ever used a glass thermometer, it usually has a red liquid in it. So that is an alcohol that has a dye in it. So that alcohol gets just a little bit larger, and the tube that it's in is very, very narrow. And so even just a slight change in volume causes it to rise within the tube. And so that's how we can measure the temperature. Old style thermostats, non-digital thermostats, so thermostat is what you tell it to be a certain temperature, and it will either turn on the heat or turn on the air conditioning in order to adjust the temperature. And so the way that it knows what temperature it actually is it has a coil on the inside, and that coil will have two layers. One layer is, say, brass, and the other one's steel. And one of them gets bigger slightly faster than the other one does. So it will start to uncoil as the temperature goes up. So we'll have like a little marker sticking out, and at low temperature, that marker will be here. Let's say that's 50 degrees. But as it uncoils and goes to 70 degrees, it will move this marker back that way. So there's, in your book, they have a picture of this. And if you want to see it in motion, underneath the picture, it says, see the video here. And if you click on it, it goes to a Wikipedia page. But on that Wikipedia page, they have the actual coil with somebody like holding up a flame to it. And you can kind of see it uncoil. So that's kind of cool. The other reason this is important has to do with lab. If something does not conduct heat very well, then we call this just glass. If I'm heating this part with my Bunsen burner, and this doesn't heat evenly, over here this is cold. Well, the good part is I can hold on to it and I'm not going to get burned, right? So the conductivity is low. But if this is also going to grow quickly, but this part isn't, that change in size can cause it to crack. So when dishwashers were first introduced, and in order to really clean the dishwashers, you use super hot water, people would put their dishes in the dishwasher, and as soon as that super hot water would blast at the dishes, it would be like putting a really hot flame on the part where the water was hitting, but the other part wasn't warming up yet, and the glasses would break. And so a lot of kitchen glassware and also lab glassware is made with a material called borosilicate glass. So regular glass breaks with a temperature change. So I had some of my inorganic students do this in lab. They heated up some glass rods and then stuck them in ice water, and the ends would just break right off. It would shatter. But if you use borosilicate glass, like your beakers and your test tubes are generally made of borosilicate glass, it doesn't conduct the heat any better, but the borosilicate glass doesn't grow very much. And so since it doesn't change size, then it doesn't break. So it has low thermal expansion. So if I have a glass dish in my kitchen and I've done like the recipe says and I've preheated the oven, so it's going from room temperature, and then I sit it on the hot wire rack in my oven that's already at 350 degrees, I really want to make sure I'm using that borosilicate glass so it doesn't heat up just the parts that are touching the rack and not the other parts. So internal energy is how much energy does an object have? It has a certain amount of energy because it's a certain temperature. It has some energy because of what it's doing. It has a certain amount of energy because of the position or tension that is related to it. In Echem, they use the letter U for this, but in your book, they use the letter E. So E and U are the same things. the change in internal energy is going to be made up of two parts, Q and W. So W very nicely stands for work. And so work is the moving part of things. And Q is the heat part of things. When we're talking chemistry, most of that work I said was done by gases. We measure that by the change in pressure and volume. So other than knowing that work is done by gases and that's measured by the change in work and volume, you don't need to know anything about work. We're not going to do anything else. Everything in this chapter is all going to be about heat. Q is what we measure as heat, and Q is not an object, not a fluid. It's not a substance that flows. So we talk about heat flow. It's not really flowing. It is a change. So usually when I am transferring thermal energy from one thing to another, I'm going to warm something up. Is that if you have two objects that are a different temperature, the thermal energy or the heat moves from hot to cold. And so this is basically saying if I have a hot thing and a cold thing, they're going to meet somewhere in the middle. I'm not going to have the hot get hotter and the cold get colder. And then we have a state called thermal equilibrium. And so I think this is in your lab manual. So you should know this term. So when I have this hot object and this cold object touching one another and they reach thermal equilibrium, what do you think has happened? They're the same temperature. That's all thermal equilibrium means. So in your lab next week, when it says, when your cup has reached thermal equilibrium, this just means that everything in the cup is the same temperature. All right, so for a given object or material or substance, the heat might be moving into, so it's getting warmer, or it might be moving out, so it's getting colder. And so we have two names for those processes, endothermic and exothermic. You've probably heard those before. When we have an endothermic process, Q is going to be positive. When we have an exothermic, Q is negative. So before we start talking about recognizing these happening in the system, it's important to recognize where you fit relative to the system. You are almost always not part of the system. We're talking about the chemicals in the beaker. We're talking about a cup of hot water. We're talking about an object, but we're not talking about you. So what are you? You are part of the surroundings. So we said the energy of the universe is constant. The universe is made of two things. Made up of the system and it's made up of the surroundings. So whatever thing we're talking about as being exothermic or endothermic, and then everything else. So that might be the beaker that it's in is part of its surroundings. The thermometer that's measuring it is part of its surroundings. You're part of the surroundings. The doorknob, state capitol, the sun, distant galaxies, all of those are part of the surroundings. Now, as far as what we can measure and what we care about, that system is probably only affecting the things right next to it. Okay, so sometimes that's you. Mostly that's going to be its container and things that are immediately around it. But because you are part of the surroundings, what's happening to you is the opposite of what's happening to the surroundings. Because if this change is always zero, then the change for the system has to be the opposite of the change for the surroundings. So if that's the case, then when something is absorbing heat, that means heat is leaving you. If I'm holding something and it's absorbing heat from me, that heat's leaving me. So how does it feel to me?
Cold.
It feels cold. So now I'm going to say caveat. If we're doing a chemical reaction that started at room temperature, then it's going to feel cold. There are times when this won't be absolutely true, but it's usually when we didn't start at room temperature. In contrast, my cup of coffee is cooling down now. So as it's cooling down, it's releasing heat, but it's still warmer than me. So since it's releasing heat out to me, it feels warm. Okay, so losing heat, exothermic, is going to feel warm. Things that are always exothermic, combustion, means setting things on fire, obviously, producing a lot of heat. Okay. And neutralization, mixing an acid and a base. Some things that could be either when I dissolve things. Sometimes when I dissolve things, they get colder. Sometimes when I dissolve things, they get warmer. So I can't really say. Some chemical reactions get colder, some get warmer. Can't really say on those. There are some things that are endothermic. Melting. So to get something to melt, I have to put energy in to kind of loosen up the solid particles and turn them into liquid, and boiling. Those are going to be endothermic. But that means if I do the reverse process is going to be exothermic. So melting ice is endothermic. So if I take ice and I put it in my hand, it feels cold, I'm supplying heat, it's going in. That also means that when ice freezes, when water freezes to form ice, it's putting heat out into the universe. Okay, so that's a little counterintuitive. Okay, whatever process is on one side, the opposite process would be in the other direction. We just don't have an opposite process for combustion.